Okay, the first thing we did was a pendulum model. Okay? Using y equals x, well, a times x to the p. What do we do with that? Well, we observed the period y at two different lengths, right? Or the frequency, whichever it was. I think it was a frequency because we counted. Okay? So we had two counts for, a count for each of two different lengths. So we put the count in and the length, we get an equation. We put the count in and the length, we get an equation. That gave us two simultaneous equations in unknowns. A and P were the unknowns, right? So we've got two data points. Gave us two simultaneous equations which we solved for A and P. Now, recently, we've learned about exponential and logarithmic functions, right? Specifically, logarithmic function. If we were to take the log of both sides of this equation, what would we get? I'll do the natural log. So what do we get on the left if we take the natural log of the left-hand side? It's really complicated, but maybe you can figure it out. And what's on the left-hand side? What do we get if we take the natural log of that? Yeah. See, I told you it was complicated. Okay? So we get natural log of y. What's that equal? Well, that's got to be the natural log of ax to the p. How do we solve that? I mean, how do we simplify natural log of ax to the p? Of course, right now you might have kind of lost track of it, but when you come to the final, you got to have in your head, you got to know the rules for logarithms, right?
Is it p times natural log?
I'm sorry, Sarah's yelling at me and I can't hear her. I don't know what it is. Anybody's talking in that room, I can't hear anything in this room. I got my hearing aids kind of upgraded and cleaned yesterday, so I can actually hear what you said. If you say it again and I don't have to listen to what's coming across the hall, yeah.
Is it p times natural log of a times x?
Well, p isn't an exponent of ax, but you've got the right idea. Okay, first of all, it's got a times x to the p. Now, how do you simplify the natural log of a product? Well, if you remember, okay, but I'm not going to put you on the spot. It's a natural log of a plus the natural log of x to the p. Right? It's just the inverse of one of the rules of logarithms. And you got to know those rules of of exponents. You got to know the rules of exponents. You got to know the rules for logarithms. That's all there is to it. Okay? Because you're going to have to use them. Okay, so the natural log of y equals the natural log of a plus the natural log of x to the p. Okay, now what can we do with the natural log of x to the p? Well, Daniel just said it. We've got natural log of y equals the natural log of a, and now we can do what you wanted to do. That's times p times the natural log of x, right? Okay? Now, if we have a value for y and x, this is going to give us an equation, right? So let's just say let's just use a little different number there, and y equals 70, and x equals 5. Okay? Then this would give us two equations and two unknowns. Okay? So then this tells us that the natural log of 105 equals the natural log of A plus P times the natural log of 2. And also that the natural log of 70 equals the natural log of A plus P times the natural log of 5. Okay, make sense? I mean, all I've done is I've replaced y and x with 105 and 2 to get this equation, 70 and 5 to get this equation. Well, natural log of 105, natural log of 70, natural log of 2, natural log of 5 are all just plain numbers, right? Okay? So we're just going to have a number here, a number here, a number here, a number here, and we'll be able to solve this system for A and P, right? Well, let's just write it out. Okay, natural log of 105. Yeah, I have to put myself on the spot. What's the natural log of 105? Well, let's see. It's around 4.7. Okay? And I might or might not be right about that. And if I'm within a tenth, I'll be amazed. But I'll be fortunate. Okay? Don't have a lot of confidence in that estimate, but we'll go with it. Okay? So let's say it's 4.7. And the natural log of 2 is, I'm going to say it's 0.7. So the natural log of A plus 0.7 times P. Okay? And the natural log of 70, now I'm going to say that that's about 4.7. Yeah, okay, 70. Okay, I'm going to say natural log of 70 is about 4.3. Not having a lot of confidence in my estimates. But the natural log of 5 I can kind of do. That should be about 1.4. Okay? Now, what can you solve this for? What can I do to both sides of this equation to solve this system? Well, 4.7 minus 4.3 is 0.4, right? Make sense? I mean, 7 minus 3 is 4. Okay? What's the natural log of A minus the natural log of A? So you should see when you look at this, that if we subtract the equation, the natural log of A is going to go away. Right? Okay? And it's just reviewing how you solve a system of linear equations, which you need to be pretty good at. So we have negative 0.7p. This is actually going to work out pretty well. So my estimates must have been, either my estimates must have been pretty good, or my choice of points must have been pretty good, or they were both pretty bad and I just lucked out. Okay? I don't know. Have to check it out. Okay. So anyhow, I solved this for p, right? It's real easy to find p. Pretty close, negative 0.57. Now really, for the pendulum, it should be negative 0.5. Reciprocal square root, which ought to be familiar to you. Okay, so anyhow, we got that. Okay, now how are we going to find A? Plug into the first equation. If you like the second one better, that's okay, but I just chose the first one. Okay? You get 4.7 equals the natural log of A plus 0.7 times negative 0.57. Okay? Well, that means 4.7 equals the natural log of A minus we get 35.4. You're close to 0.4. Okay? I can tell that from this division action, but there it is. So that the natural log of A equals what? Well, I had 0.4 to both sides. You get natural log of A is 5.1. How do you solve that? You change it to exponential form. Natural log is the inverse of the exponential function, which is A equals e to the 5.1. And everybody knows that e to the fifth is about 50 times 2.735, so say about 140. Thus, y equals 140 x to the negative 0.57. And there's our model for the pendulum. What's our alternative? Well, what I've just done here is simpler than the alternative because you know the steps for solving a linear equation. When I took the log of both sides, look at what I ended up with. I ended up with essentially a variable here and a variable here, and a number plus another number times this variable. That's a linear function. The natural log of y is a linear function of the natural log of x. So when I plugged in my 2 points, I got two linear equations. Now they're linear in natural log of A and natural log of in the natural log of A and P, but we just solved them as linear equations. So that should kind of get your attention. That's something I'm going to have you do for homework that kind of makes this point. Now, another advantage, though, of course, is that these equations are easier to solve than the equations we would get if we plug this data into this form without taking the natural log. It wouldn't matter what log we took. It doesn't have to be natural log, but since it's on your calculator, either the natural log or the LOG log is fine. Okay? If you use the LOG log, you're still going to end up with the same answer. Okay, so if I plug these points into this form, I get 105 equals A times 2 to the P. And I get 70 equals A times 5 to the P. How do I solve these equations? This is what I asked you to do for homework, but the homework got posted late. I thought I'd posted it on Thursday, but I didn't. So if you didn't get it done, do it. But some of you did it, and it looks like you did a pretty good job. Okay. How do we solve these two equations? We've done this recently. If you did the homework, I think you know. Well, we have two alternatives. It's a nonlinear equation. So we can't do what we did with linear equations. Okay? So one alternative is solve this for A. Easy to do. You get 105 over 2 to the P, right? And then replace A with that. Okay? And then we can solve for P. Now P's in the exponent. We're going to have to use logs, but we just did that last week. Okay, so I'm not going to go through the details of it. Just remind you that we have to do this. And if we get a little bit tricky about it, take the log of both sides. Turns out everything ends up being nice and linear. Okay? So what we do is either what I said, solve for A, plug into the second equation, solve for P and so forth, or you divide one equation by the other, solve for P, etc. We did both right here on the board, put one of them here, one of them here. So if you don't remember that, it should be pretty easy to spot on the website. Okay? Okay, so I kind of went off on a little bit of a tangent, but this is something I was going to do. And since you mentioned the pendulum experiment, and don't get mad at Cody for mentioning it, if you mentioned the pendulum experiment, that is the first thing we did, right? Pendulum counts. And we solved those equations. We've solved them 3 or 4 times now. Okay? And they've been assigned, so you got to know how to do that way. But this is also instructive. The bottom line is there are 2 parameters in this function, A and P, so we need 2 equations. If we have 2 data points, we get 2 equations that we can solve by one method or another. Okay, so that's the first thing we did. And then related to that, and really kind of the theme for the whole course is, we're looking at real world data and finding models. Okay, well, I've been raving on for 17 minutes, 18 now, so we'll stop this for a minute and start another one.